Hello. I'm now going to tell you the final piece of the story that I'd like to tell. It's an example that includes ethylene and humble rock salt, and that is the chlor-alkali industry, because wherever you see salt, you will see the chemical industry. I would love to talk about polythene and about all the other ethylene derivatives that happened. I mean, there are so many of them, but time is so tight. And I'd rather focus down on chloroethylene derivatives because they are so important. Now, due to my safety expertise, when I used to work at Billingham, latterly with some of the hydrogen cyanide processes, I was often called in to consult on other sites with high levels of hazard. And over in the northwest of the United Kingdom was such a site, because not only did it handle chlorine, but it also handled hydrogen fluoride, quite a toxic cocktail. This site was pivotal for producing initially polythene, polyvinyl chloride, refrigerants, anaesthetics, solvents, and so on and so forth, and I'll tell you more about that in a minute. In the early days of this site's operation, ethylene was actually transported by road tanker from the naphtha crackers at Wilton over the Pennines for its use down in the town of Runcorn. It's quite mind-boggling when you think of the hazards associated with ethylene. It's very unstable and highly flammable. So when the Trans-Pennine pipeline was commissioned, it was a great relief for everybody, and safety was much improved as a consequence. The site I want to introduce to you was old even when I was an engineer, because chlorine production started there back in the 1890s, thanks to Hamilton Castner and Carl Kellner's introduction and invention of a clever process involving liquid mercury and rather a lot of electricity to convert salt water into chlorine. Now, let's go back a few steps in the food chain to start with. Let's remind ourselves about ethylene production. Here on my blackboard, I'm going to put two blocks for you. There's steam cracking of naphtha. We've talked about this before. This is my first block. Steam cracking of naphtha is predominantly used to make ethylene, and that's what we're going to talk about now, because last time we met, we talked about pyrolysis gasoline and benzene and toluene and xylene and how important they are. The other route to ethylene that's quite important is the gas cracking of ethane. As and when natural gas became more common as a chemical feedstock, ethane gas cracked into ethylene became one of the major production routes. It's a very different production route compared to steam cracking of naphtha, because it doesn't produce a product such as pyrolysis gasoline, and as a consequence the amount of high value chemicals that ethane gas cracking produces is a lot less. Ethane gas crackers are still a pretty impressive piece of plant. Here on the blackboard I've pinned up a photograph for you of the Fife gas cracker at Mossmoran, just north of Edinburgh, which was built long after I retired in 1985. It takes ethane from North Sea gas, cracks it into ethylene, and then puts it into the UK ethylene distribution network. I'm not going to talk about Mossmoran this time around though. What I do want to talk about is a site in the northwest of the United Kingdom, in Cheshire, on the banks of the River Mersey, in the town of Runcorn. This is a site I have a lot of fond memories of, and it's old. Chlorine production started there in 1897, and it was located here because underground, underneath Cheshire, is one of the largest rock salt deposits in the entire of Europe. It's the remains of a dried out sea from the Jurassic period. Also, this site is close to deposits of fluorspar in the Peak District, and considering that hydrogen fluoride is one of the intermediate chemicals produced on this site, it needs a source of fluorine. Pragmatically, this site is bordered also by two canals. The great big Manchester Ship Canal, ideal for transporting goods and material and equipment, and the smaller Weaver Navigation. There's good rail links since the Victorian era into this town, and again, much like in the northeast, a ready supply of very good workforce to work on these chemical plants, to become engineers, and to do all the other supportive operations that a massive integrated chemical site needs. A few photographs for you. At the northern end of the Runcorn site, close to the Manchester Ship Canal, in fact this photograph was taken by a friend on the Manchester Ship Canal, we see the main chlorine processing part of the works. There's 2 more Horton spheres for you. We saw Horton spheres on the ethylene plant at Wilton. These Horton spheres, however, don't contain ethylene, they contain chlorine and are hence highly hazardous. And you can see in the background miles and miles of chemical processing plant that make all the various intermediate products from chlorine as one of its raw materials. As you walk down through this site for a few miles, you get to the southern end of site, and I've pinned a photograph up on the board there for you. And this is where all the fluorine processing takes place. The plant you can see in the immediate foreground is, in relative terms, compared to my experience, a brand new hydrogen fluoride plant. It's a 6th generation of hydrogen fluoride plant on this site. The older ones weren't quite as shiny and nice as this one. And this site, the Rock Savage site, used to produce refrigerants. By and large, these days it only produces one, 134A. The old days, this used to produce all the chlorofluorocarbons which were rightly outlawed by the Montreal Protocol in the late 1980s. I'd like to give you a brief example of how this site is a food chain, one plant feeding another now. So, in diagrammatic form, I want to raise your awareness to 5 different products. Dry cleaning fluid, which is going to be in orange, solvents in brown, refrigerants in green, polymers in red, and anaesthetics in blue. So, we start from common salt, extracted from underneath Cheshire by a combination of solution mining and physical mining. A lot of electricity goes into the production of chlorine. It's an electrochemical process. As a byproduct, hydrogen is also produced. Each little square blue block that I'm putting on is an individual plant. So, the square blue block that involves hydrogen and chlorine produce hydrogen chloride. Other byproducts from this electrochemical process include what is nicknamed hypo, sodium hypochlorite, which you'll know as bleach. Also sodium hydroxide, which some of you might know as caustic soda. Those are all byproducts from the chlorine production process. If we follow the solvents food chain a little bit more, what we find is that we had methanol. Methanol is imported from other sites, and we find that we can produce chloromethanes when we combine that with hydrogen chloride, or chloroform, or carbon tetrachloride. Now, if we bring in fluorspar, and if we bring in sulfur, we can make sulfuric acid and hydrogen fluoride. We make hydrogen fluoride from reacting fluorspar with a mixture of sulfuric acid and of oleum, fuming sulfuric acid. Quite an inherently hazardous process because of the chemistry. Hydrogen fluoride, a plant that I used to know very well, the operators used to describe this as an abhorrence of nature. Hydrogen fluoride is horribly, horribly reactive, but it can be used to make all sorts of products, and we'll see in a minute. Looking down the chlorine route, if we import ethylene, the site sits on the end of one of the branches of the Transpennine ethylene pipeline. We see chlorine reacting with ethylene to make dry cleaning fluid, perchloroethylene, also trichloroethylene, an industrial solvent. With a little bit of polymerization, you can make polyvinyl chloride, there in red. Also, we can make 1,1,1-trichloroethane, which used to be an almost ubiquitous solvent prior to the Montreal Protocol coming into effect. And so we can see that from chlorine and from ethylene and from methanol, we can make a very large number of different solvent-based chemicals. Now, let's expand the fluorine route a little bit more, because we'll react carbon tetrachloride and chloroform with hydrogen fluoride, and we produce refrigerants. The old CFC refrigerants at the bottom of that picture, R22, used to be called Arcton 22, R11 and R12, very common low temperature industrial refrigerants. And at the top of there, the CFC replacement that was introduced in the mid-90s, which was HFC 134A. Sadly, turns out to be a very potent greenhouse gas. Now, if we take refrigerant 22, we can do some polymer chemistry and make polytetrafluoroethylene, known to you probably as Teflon or non-stick. Now we need one more ingredient. We need bromine to produce halethane, which is an anaesthetic from a combination of hydrogen fluoride and trichloroethylene. Bromine was harvested from seawater nearby on the Isle of Anglesey in Wales. And so this diagram here gives you an idea of the integrated network of an integrated chemical site based on chlorine processing and ethylene predominantly. A vast number of chemicals produced for a very complex set of plant. I mentioned at the outset that the production of chlorine is an electrochemical process. This final picture I've pinned to my blackboard here is of the old power station that used to provide that electricity for the chlorine electrolysis back from the 1890s onwards. This power station is now disused. It was only 100 megawatts in capacity, but at the height of production of this site, even that power station still was not enough, because the entire site had an electrical load of 400 megawatts, which is about 1.5% of UK electrical generation in your era. So this is a very good example how engineers need to work side by side with one another. Chemical engineers with electrical engineers, with mechanical engineers, with control engineers, with safety engineers, to make these big, heavy production sites viable, feasible and safe. A few key points from you. So wherever you find salt, you will usually find the chlor-alkali industry. When you combine chlorine with ethylene and methanol, you can make a huge range of products. Much of these in your era, however, have now been phased out due to their environmental concerns. The electrolysis of chlorine is a very good example of a heavy-duty electrochemical process, and electrochemical processing will probably be something that you in your era will develop a lot further. It's also a very good example of a site that has a very large electrical load, 1.5% of typical UK generation. Well, I've got to go now, so I hope that you found this small session of lecturing very interesting. I hope it's given you some background into the chemical industry that you might see today, and hopefully it's given you a bit of an understanding into some of the key processing routes that the chemical industry has grown up around. So I shall bid you a farewell, and maybe one day we will bump into each other.